start. I'm Mario Inciosa, Principal Software Engineer with Microsoft, and I'm going to be talking about building a scalable data science platform with R. And I'd like to thank everyone for coming to the last session, last round of sessions here at Hadoop Summit. Great to see the attendance here at the end of the conference. So I'll start off by talking a bit about R itself, and then I'll go into how we integrate it with Hadoop and go through a live demo for about the second half of the talk. So what is R? Well, you probably are familiar with R if you're coming to this session, but if not, it's both a language and a platform. In fact, it's the most popular statistical programming language. It's also a powerful data visualization tool, and it is open source. It has a really thriving community with over 2.5 million users, and it's being widely taught in universities, so it's a skill that a lot of new and recent graduates have and like to use. In addition, there's a thriving number of user groups worldwide. Almost every major city has meetups in R. Also, there's a great ecosystem that's built up around R. With all these users, they're also contributing packages. R is very extensible, and it has now over 8,000 high-quality packages that have been contributed to what's called CRAN, or the Comprehensive R Archive Network. So this greatly expands the power of the core base R with these extension packages, and it has allowed really rich application and platform integration for the R language. So common R use cases really are very much have a lot in common with Hadoop use cases. So it's very appropriate that we're talking about it here. They span lots of verticals. Retail, financial services are a couple big ones. Of course, healthcare is very interesting, and manufacturing, really right across the spectrum. Well, our adoption is on a tear, we can say. It's gone from being the 9th most popular language, according to IEEE Spectrum, to now the 6th highest language on that ranking. In fact, it's the highest language on that ranking of any domain-specific language. All the other ones above it are general-purpose languages. So really great adoption. But we do find that open source R has some limitations when it comes to the enterprise. For one thing, data flows can overwhelm open source R. Because the base R package, the algorithms in there are designed for in-memory operation. So they basically stop working if your data exceeds what you can hold in memory. And they're also not designed with parallelism in mind. So they're essentially using one core of your processor. Finally, since they weren't designed initially for big data, they can incur expensive data movement, and often in the course of performing a calculation may duplicate the data, therefore further limiting the size of data that you can process in the RAM of one node. Also, they don't provide, enterprises often want levels of support and SLAs, and that's not provided with open source R. What Microsoft is doing is bringing solutions to solve those gaps for the enterprise. It provides peace of mind by providing support and SLAs, and added efficiency and speed and scalability by including with our extension packages that include very efficient implementations of key algorithms, and also scalable and distributable implementations of those algorithms. We're also providing flexibility and agility by providing a set of functions that work with big data regardless of the platform that you're using. An example of that is shown here in the next slide, where we see that our server technology in Microsoft R allows you to essentially write your R scripts once and deploy them anywhere. The same script that you write to run in the cloud can run in a Hadoop or a Spark cluster, or in a data warehouse, or on a desktop or server. We're covering both Windows and Linux servers on-prem in the cloud. We run in HDInsight, Microsoft's in-cloud Hadoop platform. On-prem, we run on Hortonworks, Cloudera, and MapR. And as far as data warehouses go and databases, we run inside SQL Server 2016 and Teradata database. This is an example of how portable your R code is using these functions. Here I'm showing the script for performing a computation, a model fitting computation using R in a MapReduce environment. We start off by defining what we call our compute context, which is telling our functions where we want the computation to be performed. In this case, we say set compute context rx Hadoop MR, which says use Hadoop MapReduce to do the computation. Then we specify what data source we want to use. In this case, we say it's text data, happens to be a CSV file that's stored in HDFS. And then once we've specified where we want the computation to be performed and what data source to use, we specify what computation to perform. In this case, we call the rxLogit function, which is a logistic regression fitting function. Now, suppose we wanted to move this from MapReduce to Spark. Well, normally, if you coded to a MapReduce API, you'd have to completely rewrite it to a Spark API. But using this library, it's really a matter of just changing that one line that specifies the compute context. So now instead of saying rx set compute context Hadoop MapReduce, we say rx set compute context rx Spark. And the rest of the script can remain as it was. This also applies to the other platforms I mentioned, such as database platforms. So it's important to remember that although we've included these additional packages, our server is still 100% compatible with open source R. We've got a wide range of scalable functions, which I'll talk about in a little more detail, but we also have the ability, with that 100% compatibility, we have the ability to parallelize virtually any R function from any R package. So this is a list of the scalable distributed algorithms, which we call parallel external memory algorithms, that we include with our server. And they span a range of functions, starting with ETL functions, your descriptive statistics, then the predictive statistics and machine learning algorithms, as well as clustering algorithms, algorithms to support performing Monte Carlo simulation, and then the functions for custom parallelization. When you have an R function that you've written or an R function that you want to use from one of those CRAN packages and you want it to run in parallel over a distributed infrastructure, then you can use those custom parallelization functions. So here I'll go into the architecture a bit of our server when it's running on Hadoop. I'm going to start by mentioning our server running on the edge node of the cluster. So we have the R engine running there, and we can do local processing on the edge node. Our server has the ability to either copy data from distributed storage to that edge node, or to stream data from the distributed storage to the edge node, and then process it on the edge node. And then this is an appropriate way to go if you are working with a relatively small amount of data that you can process on one node. Then when you scale up to larger data, you can use the second mode, which is distributed processing. In this mode, there's a master R process running on the edge node, and then it uses Apache Yarn and Spark to invoke worker R processes and communicate with these worker R processes running on the data nodes. Each worker process will process a portion of the data and produce an intermediate result. Then those intermediate results will be combined and returned back to the master R process on the edge node. Then that R process can either return a final result to the user, or in the case of an iterative algorithm, it can initiate another pass over the data. There are several ways to connect to that edge node. There are actually many ways. So from your client machine, your desktop, you can open an SSH terminal to the edge node and use R at the command line. You can start up R on your client machine, on your workstation. You can use the recently announced free Microsoft R client or Microsoft R server on your workstation and have that make the SSH connection transparently to the edge node. And you can use our new IDE that we are offering in our tools for Visual Studio, which works with both the paid and the free community versions of our Visual Studio. So we've got our tools for Visual Studio as another IDE with a lot of nice features for debugging and remote execution. You can also do this all from a web browser without adding any additional software to your workstation. You can use the community edition of RStudio, and that will allow you to have a full IDE environment for R in your web browser. I'll be showing that in my demo. Another approach with a web browser is to connect to Jupyter Notebooks. And finally, it's possible to have BI tools and applications access the R on the Edge node through a technology we call Deploy R, which is a web services SDK that we provide that allows you to invoke R functions by making web services calls. So that's very useful for integrating with other applications in the enterprise. Now, I'm going to talk a little bit about how we can do this in the cloud. Of course, Hadoop can run on-premises or in the cloud. If we're interested in running in the cloud, we can use a recently announced capability, which is HDInsight plus R server. So this essentially gives you managed Hadoop for advanced analytics in the cloud. An HDInsight cluster is a Hadoop cluster in Microsoft Azure. It's very easy to set up. I'll give you an example of that in the demo. It's elastic, so while it's running, you can add or remove nodes. And it provides SLAs. It provides 3 nines of connectivity so that you don't have to worry that your cluster is going to become unavailable. It also includes Spark. The latest version of Spark is included, 1.6.1, and R server in this premium version of HDInsight. So using R and an HDInsight cluster, you have 2 APIs you can use in the Spark environment. You can use the Spark R functions, which include a lot of great data manipulation functions, and increasingly machine learning functions are being added there as well. And you have the RevoScaleR functions, which are the portable functions I've been talking about, which work on a number of different distributed platforms. Both of those APIs will then call into Spark and Hadoop. And when you're working in the cloud, then those Spark and Hadoop jobs can use data from blob storage and data lake storage, which are persistent storage services that don't go away when your Hadoop cluster goes away. So you have this flexibility to turn off your cluster, just delete your cluster when you're not needing it. Your data will still be waiting for you in blob storage. An example, I've talked about a bit about scalability, and we wanted to show that, yes, we can scale we can take this approach and scale it really very, very far out. So this example shows how we can scale to hundreds of nodes and billions of rows and terabytes of data. So we're using that logistic regression function I showed earlier, the RxLogit function, and we're applying it to a public data set, the New York City taxi data set. And we're showing how we've plotted billions of rows in the horizontal axis and elapsed time in the vertical axis. And you can see a linear scaling of time as we increase the number of rows. We did it out to 2.2 terabytes, but there's no reason why you have to stop there. So now I'd like to talk about a typical advanced analytics lifecycle. In advanced analytics, very often we start off with we have these 3 stages. First, we're preparing our data that we want to use for machine learning and analytics. We'll assemble the data sets we need, cleanse them, perform transformations, maybe explore them, perhaps even join multiple data sets. Once we've prepared the data, then we can go on to the modeling step. In the modeling step, we're going to build statistical and machine learning models, for example, classifiers and regression models. And we both fit models in this stage, and we then test those models to evaluate their performance, and we may iterate on the architecture of those models and choice of model to get the required and desired performance. And once we have the model that we want to use, we then usually want to go to the 3rd stage of operationalizing the model. making the model available to perform predictions and generate visualizations to support business applications. I'm going to now do a demo, which is an easy-to-understand problem of trying to predict airline arrival delay. And this model, actually, can I stay on the slide for one more minute? OK, this model will have three components. This demo will have three parts to it, corresponding to those three stages I talked about in the previous slide. We'll have the cleaning and joining stage. And for that, we're going to use the Spark R functions provided by Spark running from our server. Then we're going to go into the second stage of creating the model. And that's going to be done using the scalable R server functions, the ones that start with Rx, like RxLogit. And finally, we will go and deploy the model. And to deploy the model, we're going to use another open source package called the Azure ML package, which is a package that's able to deploy R functions as web services in the cloud. So now if we could, I think we're now ready to switch to the demo. So here I am in the Azure portal, and this is where you interact with all of your tools in the Azure cloud. And I want to demonstrate how we would provision a cluster. We would click on New. It's a quick process. We choose Data and Analytics, and then we will select HDInsight. This was very quickly shown during the first keynote, the first day of Hadoop Summit. And once that's loading, and hopefully have a quick connection here, I can enter a name for the cluster and specify the type of HDInsight cluster I'd like to use. And in this case, we want to use an HDInsight cluster that has our server installed on both the edge node and the data nodes. So that's a new feature. It's in preview right now. I will select that as the type of cluster. Then I enter my credentials. I give a username and password for the admin. And I specify a username for the SSH user. And I like to use a public key instead of a password. So I'll just click on public key. And that will allow me to enter a public key. Next, I choose the data source. I mentioned that we can work against data that is stored in blob storage. And I have my airline, I have my data for my demo in blob storage. So I will select my storage account and the subscription under which I stored my data. And we have many storage accounts, so a long list will be generated, and I can just type in the first few letters, and I find my storage account where my data is waiting for me. So I'll be spinning up a brand new cluster, but it'll be able to use the data that I already have stored in the cloud. And I'm going to do one more step. I'll just demonstrate how we can use this optional configure. Oh, I skipped the pricing step. In this step, you choose how many nodes you'd like to have in your cluster. It defaults to 4. You can put any number in there. Let's say we want to have 10 nodes. We can also select the worker node size. I can select, for example, let's take 8 core nodes with 56 gigs of RAM per node. Once I've selected that, I have my choice of selecting the head node size and the size for the node where our server, the master process of our server is running, and it will show me what is the cost of that configuration that I've selected. So I just go ahead and select that. Now I'm going to go to the last step, optional configuration, and here we have the ability to further customize things by running script actions. These are bash scripts. And one handy script is a script that we provide for adding additional R packages to every node of the cluster. So I can just give it a name like packages. I can paste in that URI. So in our documentation, we provide you with a link to the install R packages script. And you can customize these scripts as needed. So I'm going to tell it to run that script on every worker. And this also takes parameters. So I'm going to tell it to install the string R package, which is an R package that provides additional string functions. So that gives you a lot of flexibility for configuration. And then once we've made our configuration, takes a minute or two, as I've showed. We could also script this. Once we've done that, we just hit create, and now the cluster will be created. Oh, and I forgot to specify a resource group. I can use an existing resource group. This is a way of organizing your resources so that you can easily find what your charges are for a group of resources or delete those resources when you're done with them. Now, let's take a look at a cluster we've already created. In this case, I want to show you two features. Once you've created a cluster, you have that ability to scale the cluster. As I mentioned before, we can just change the number of nodes here to scale up or scale down the cluster, change the amount of power we have available to us, and also what the charges are. And another thing I'll point out is the cluster dashboards. This is a handy way to access Ambari, which is behind this HDInsight cluster dashboard, to open up Jupyter notebooks, or to access the Spark history server, or the Yarn applications page, all nicely available through this interface. OK, so now I will so I actually skipped a slide or two. I think I went to the demo 1 or 2 slides early. Is it possible to switch back to the slides? OK, great. Because I wanted to show you 2 slides just about the data that I'm going to be using in the demo. There's an airline data set we'll be using, which is flight on-time performance data. It's a government data set, covers over 20 years, over 300 airports. And it's interesting, it's got data for every single carrier, every commercial flight in the US over those decades. And the second data set we're going to use is a weather data set. And this data set has hourly weather observations for over 2,000 weather stations. Great. So now we can go back to the live demo. So as I mentioned, there are many ways to connect to the cluster. We're going to use SSH. I've typed the SSH command to connect to my cluster. I've specified a private key, and I'm also specifying port forwarding here. We'll see that that allows us to use RStudio server in a web browser. But I'll also show you that even without RStudio, we can just type R at the command line, and we can start entering our R commands. However, it's really comfortable and convenient to have the full RStudio IDE. So through port forwarding, I just point my web browser at localhost 8787, and now going through that encrypted SSH connection, I'm connected to RStudio running on the edge node of the cluster. Now, I've broken up my scripts to correspond to those 3 stages of the typical advanced analytics lifecycle. I'm going to go through those scripts, and I'll start with a script that I used to set what we call the compute context in our server. As I mentioned before, we can use data stored in HDFS compatible storage. We can specify that our file system is RX HDFS file system. Or if we want to use data stored locally on the node's native file system, because maybe we have smaller data, then we can use the native local file system by using the RX native file system function. Similarly, we can change where the computation happens. We can do distributed computing using Spark by calling the RX Spark function. Or if we just have single node computing, we can call RX local SEQ, and then it doesn't use the Spark mechanism, it just runs the computations on the edge node. Next, I'm going to move to that first stage, which is the cleaning and joining of the data set. And here I'm going to use functions from the Spark R API, which is an API from Apache Spark project. So I'll source my set compute context script. I'll load the Spark R library, and I will start a Spark R compute context. Next, I'm going to specify the path to my airline data. It's a directory full of CSV files. And I will specify the path to my weather data, another directory of CSV files. Now with those paths, I can call SparkR's read.df function, which this will create a SparkR data frame, which is an in-memory representation of the data. So I'll do that both for the airline data, and I'll do that for the weather data. And now that we've created these SparkR data frames, there are quite a few functions available to us for data cleaning and transformation. There's a rename function we can use to change the names of the columns. We have a select function to select desired columns, so we don't need to work with all the columns. And we can do simple math operations in the, using this API. So we could, for example, divide every one of the hour values by 100 and take the floor of it to round down to the full hour. We can even do grouped aggregations. We can do this function will do an averaging of the weather readings by hour. So if we have multiple weather readings for a particular location and a particular hour, we can average those together. The most important thing, I think, is the big data join. And we're going to use SparkR's join function to join the airline data with the weather data at the origin airport, because presumably the weather data will help us make a better prediction. And we're not only going to use the weather data at the origin airport, but we're going to do a second join where we join with the weather data at the destination airport. We've just changed the join condition, so now we're joining data that matches the destination airport ID. And now that we've created this transformed and joined data set, we can go ahead and output it to CSV. So I'm going to call SparkR's write.df function, analogous to the read.df function, that can write out all this data to a directory of CSV files. And now that I'm done with SparkR, I can stop the SparkR compute context by calling the stop function. So now we're going to read that data that we've written as CSVs. We're going to import it into our server's compressed binary format called XDF. And to do that, we start by specifying the schema of the data. This can be left to be inferred, but it's often good practice to specify the schema so you don't have any surprises. And then we specify that we're working with text data as the input, and we want to produce the XDF data as the output. And we call the rximport function to do that. And once we've imported that function that data into the binary format, we can call the getinfo function, and we can see, for example, that this is now represented by 80 binary files that comprise 148 million observations, 22 variables. And for each variable, we see the name of the variable and information about that column, such as low-high values. And in the case of categorical or factor variables, we can see what the factor levels are. So we see that, for example, for year, we have 26 distinct years in the data set. So now we've done all of our data preparation, and I'm going to move on to the middle step, the modeling. And in machine learning, we typically divide our data into training and testing sets. So we train on the training set, and then we test on the test data set. So this data set goes up through the year 2012. And what I'm going to do is train on all the years before the year 2012 and then test on the year 2012. So I'll use the rxDataStep function, which is one of these scalable functions in our server, to select all of the rows where the year is not 2012, and that'll be my training data. And similarly, I'll use the rxDataStep function to select only the year 2012 rows, and those rows will comprise my testing data. And now that I've selected the training and testing data, I can build a logistic regression model. I specify the formula for my model using R's familiar formula language. So these scalable functions use the same formula language that the built-in base R functions use. In this language, you specify the target variable, the variable you're trying to predict. In this case, rdel15, which means arrival delay 15 minutes or greater. We specify that to the left of the tilde sign, and then all of the variables to the right of the tilde sign are the variables we're using for prediction. For example, whether, what day of the month is it? December 25th or January 1st may be very particular days, so we want to include that information. We specify the day of the week. It makes a difference whether you're flying on a Monday or a Friday as far as delays go. We include the carrier, origin and destination airport, and all these weather variables that we've joined. So to perform that model building, we call the RxLogit function. And we can take a look at the model that's created by the RxLogit function. And it has many parameters with their coefficient values. We see these are the weather-related variables here at the bottom of the list, and they all have 3 stars next to them. 3 stars means that that's a highly significant parameter of the model. So it's good that we included the weather variables in our model. Next, we can test the performance of our model. And to do that, we're going to call the RxPredict function, which is analogous to the predict function in base R, that will run the model on the test data and score the test data. And then we will compare the scores to the ground truth, and we will be able to compute what is the accuracy and another measure called the area under the receiver operating characteristic. So I can plot that curve. And the receiver operating characteristic is a curve where the higher this curve, the better the prediction. If this curve were just a horizontal, a diagonal line, and the AUC were 0.5, that would just be like predictions equal to chance. Anything above 0.5 is better than chance prediction. So we do see that we are able to make a better than chance prediction, but we're not able to make a perfect prediction because there are many other variables involved in whether a flight is delayed that are not included. It's also easy to create other models. We just did a logistic regression, but there's a whole suite of functions we have. So we could create, for example, a decision tree model just by going through the same steps. And now I'll go on to the last stage in that 3-step process where we want to operationalize this model and deploy it as a web service. So for that, we're going to, as I mentioned, use a package called Azure ML. But first, I'd like to note that the Azure ML package uses the Azure Machine Learning service of Azure. And that service right now is still running open source R. It doesn't have these additional R server functions. So we need to convert our R server tree model into an open source R model. And that's done by this line here where we call the asRPart function. It converts the model into an object which is compatible with the RPart library in open source R. And then we create our scoring function, which is just a 2-line function where we just specify that we're going to be using the library, the RPart library, and we're going to be calling its predict function. This is familiar to our folks. And now let's try out that function. First, we'll test the function locally. So we'll put some example data into the scoring function. And just on that edge node, we're just going to evaluate that scoring function. And we get a bunch of scores back right away. So that's good. Now we're going to publish the scoring function as a web service. And to do that, we load the Azure ML package that I mentioned, this open source package. And then we call its publish web service function. So this will create a new web service that's a scalable web service in Azure. And you can see the web services you've created by going to Azure Machine Learning Studio. And here you can see delay prediction service. I published the service earlier this morning. The service, if we click on it, we can get more information about the service. I haven't visited this page in a couple of hours, so I see I have to allow it to reload. But when we go to this, this page, we can see all sorts of help for our Azure web service. It'll even show us sample code. So if you're not quite sure how to write an R or C# function to call that web service, we just go to the help page, we click on sample code, and we see C#, Python, and R code for calling this web service. In fact, for calling the web service from R, it's particularly easy because there's a package provided in the Azure ML library for that. Not a package, but a function. It's called the consume function. And if I run that consume function, it's going to hit that web service, and it's going to return scores. And we can print out the scores and see that we did indeed get scores out of that service. So that's the end-to-end demo where we did everything in a scalable fashion from our server. And now we can switch back to the slides. So I'm running out of time. I'll quickly move on to one other example, which is a genetic disease risk example. And the reason why I'm even mentioning this example is, besides it being an interesting example, it's a good example of the fact that this applies to really any R functions out there. This genetic disease risk calculation was done using a package called Variant Tools, which is an R package provided in the Bioconductor repository. And this Variant Tools package was written without any knowledge of R server or Hadoop or the cloud. But because we have functions in R server to run any R function in parallel in Hadoop, we can run this now at scale. We can use it to process terabytes of genomics data, and we can even run it in a geographically distributed fashion in data centers all around the world, thereby allowing data to remain within a region where it's generated. So we see that really there are 4 trends that are coming together that are allowing us to create applications such as we've seen. There's the big data trend, providing us with the data sets we use, such as the genomics data. There's the open source trend, where we're using the open source R engine. We're building upon that engine. We're using Linux on the nodes of these servers. We're using the Hadoop and Spark packages. Then there's the data science trend that has brought us things like R and these graduates of universities who are now very talented in using the R language. And finally, there's cloud computing, where I was able to spin up a cluster and create a web service at just really using a click. So finally, for more information, you can visit the Microsoft websites. And after that, I'd just like to thank you for coming to the last session. And I see we do have a few minutes left for Q&A. Yes, please. The question was whether this works against a Kerberized cluster, and yes, it does. So if you have a Kerberized cluster, Hadoop handles Kerberos so seamlessly that there's very little we had to do to allow it to support Kerberos. Yes?
So to use Spark, the minimally is R required to install only in the master node or in every worker node?
Okay. Right. Question was whether R gets installed only on the edge node or also on the worker nodes of the cluster. Yes. So R doesn't need to be installed on like the master or head nodes, the nodes where you have, for example, the name node, but it does need to be on the edge node because that's where the master process is, the R master process. And then because it's able to run R functions in the cluster, it needs to be installed on every worker node. And so that's what happens for you automatically with HDInsight. It gets installed on all of those nodes. So it's a little this is a little different than the approach you have with the Spark R library, because the Spark R library doesn't actually run R inside Spark at this time. It's more of a wrapper which allows you to call Spark functions from R. But if you actually have a complicated R function that you want to run inside of the cluster, you can do that with this setup, because we have R interpreters on every node of the cluster. Yes?
So if you have applications or tools, does it need to be running on S node or somewhere else?
An application that uses R, the applications don't have to be running on the edge node because they can be using, for example, the deploy R component I mentioned, which is exposing these R functions as a web service. So they can be on other nodes, and they're using web services to contact the deploy R server, which then runs their function for them in R. I saw a question over on this side of the room.
So compared to the open source R and the available functionality, and how does Spark R compare to the open source?
Right. So open source R, and so open source R, the base R doesn't really have functions for Hadoop. There are contributed packages for Hadoop, and then there's the Spark R package, which is also open source and included in Spark. So they differ in the exact set of functions that are available. Right now, Spark R is starting to add the functions of MLlib to its API. As of version 1.6.1, it's just one function, but they've added 3 more in version 4. So that's growing, and they also have join function. There's also a slightly different philosophy between the two packages in that, like, the Spark R package is designed for Spark, but the Scale R functions I was mentioning aren't designed only for Spark. They're designed to work with Hadoop MapReduce and databases, as well as running on the multiple cores of a single node. So that's kind of that write once, deploy anywhere approach. And that's a third question. Okay, to add new packages, I'm not quite sure. I think you'd have to add, two approaches you can take. One is you could add the new packages to each node of the cluster as it is, or you can create a new cluster and specify additional. Right, right. So you want to have an automated way to do that. Right. Ah, right, right. So it varies a little bit from cluster to cluster, whether you're using Ambari, or if you're using Cloudera Manager, you have some different options for versioning. Generally, we want to have one version across the cluster. Right, right. So if you wanted to upgrade the version of R, that's pretty much at this stage, it's a process of, if you have an on-prem cluster, it would be a process of, I think, removing the current version and installing the new version, basically. There isn't just like an upgrade function. Yeah. In the cloud, it's a little different because you just create a new cluster. Mm-hmm. Right. And I think we're running out of time, but let me take one more question. Yes.
You have to have the ticket on the edge node.
Yes.
The workstation ticket doesn't transfer to the Kerberos.
So, good question. I believe if you're using SSH, it will transfer, but correct me if I'm wrong on that. Thanks. Thank you. Thanks, everyone. I think we're out of time, but please come up, and I'm happy to answer additional questions.